Greetings. My name is Professor Stephen Miller. I am a professor at Williams College. I'd like to welcome you to the units from the LACOL Data Science Summer Class on Linear Regression. So what I'm going to do in the first lecture is talk about some of the general theory, and then this will lead into how we can extend it to more complicated and interesting examples, and then talk about some applications to real-world problems. So first, let's share the screen. Okay, so to begin with, imagine we have a set of data points and we have some values of X and we have some values of Y. And the goal is to try to figure out what is the relationship between X and Y. Now, if you look at this, it looks pretty clear that this should be some kind of linear relationship. I should be able to draw maybe some kind of good straight line through the data. And the first part of regression we're going to look at is how to find the best fit straight line. We'll see that the word best actually has to be defined, that depending on how you look at things, there will be multiple lines that, with different interpretations, can all be considered the best fit. Now, something on this plot should give you pause, and it's the axes. So this is one of my favorite comic strips from a great site, XKCD. So you have two people talking. I think we should give it another shot. We should break up, and I can prove it. You see a plot of their relationship. And the first person goes, huh, and goes, maybe you're right. And the second person says, I knew data would convince you. And this is a data science class. We want to be able to convince people with data. But the first person then remarks, no, I just think I can do better than someone who doesn't label her axes. And so this is an extremely important point to remember, that when we are doing our analysis, at the end of the day, we're not just doing it for ourselves. We want to be able to tell a story and convince someone else. A picture's worth 1,000 words. You should have heard this many times. A really good image can illustrate a concept beautifully. And to do this properly, we need to have units. We need to have our axes labeled so you can quickly look at it and see what's going on. So let's draw it again. And now I'm going to label the x-axis in displacement in meters and the y-axis the force in newtons. So we have a spring, we're stretching it, and we're seeing what is the force. And so I chose the data where I chose the x-ends to be moving in increments of 0.2. I chose the y-ends to be just 5 times x-ends. So if you know Hooke's law, the force is equal to k times the displacement, where k is some constant. I chose my constant to be 5. And then I chose an error to be randomly drawn from a normal distribution with mean 0 and standard deviation 4. And so if we do the standard linear regression, we're going to get a best fit line of 4.99x plus 0.48. So if we're trying to find y equals ax plus b, we get a equals 4.99 and b equals 0.48. Considering that we chose y to be 5x, we see we're doing a great job with a, but not such a good job with b. And so the question is, why is one more accurate than the other? How can we trust, or how much can we trust the results that we get? So our value of b is significantly off, as was remarked. Now, there's other ways. So we use the method of standard regression, which we'll talk about, that uses squares to measure errors. And we'll talk about this in greater detail soon. If instead we used absolute values to measure errors, we would get a best fit line of 5.03 for A, and the best fit value of B is less than 10 to the minus 10. So the point of this is to just highlight the fact that there can be multiple answers to a problem, and it depends on what you want to look at. So the difference, as I said, is coming from how we are going to weigh the errors. And we will discuss this in great detail very, very soon. So if you want to see more details with this written up with some text, attached is a link where I have a nice description of what I'm about to talk about. So the idea is to find the best fit parameters. We want to choose the values of A and B that minimize error in some kind of conjectured relationship between Y and X. So let's say we observe values of yi with input xi, and we believe that they're linearly related. So that means we believe y equals ax plus b, so yi should be axi plus b. So there are 3 natural choices for errors. We'll call them error 1, error 2, error 3. And they're going to be functions of 2 variables, a and b. So the first is the simplest. We take what we observe, and we subtract what we predicted. The second is we take what we observe, we subtract what we predicted, and we take absolute values. And the third is, instead of taking absolute values, we take the square. Each one of these has a point in its favor. The first is the simplest. We just look at observed minus predicted. The problem with that is a positive error can cancel out a negative error. So imagine you have just 2 points, one at the lower left corner, one at the upper right corner. You might say the best fit line between them is the straight line that connects them with no error. But if I went the straight line in the opposite direction, the positive error here would cancel with the negative error over there. So first one is right out. Let's look at the second one. We use absolute values. Absolute values is nice. It's not so hard to use, especially if you're using a computer. But the problem is, mathematically, we don't have as many tools available when we use the absolute value. If we use the square function is differentiable, the absolute value function is not differentiable. And this difference is meaningful. And because of this difference, we can use calculus to get explicit closed form expressions. But as we saw earlier when we looked at the best fit values for our spring problem, we saw 4.99 and 0.48. We saw that there were some issues in terms of getting the best fit values for both. We saw that the absolute value actually gave a little better value for both A and B. But there is a tremendous advantage to having closed form expressions. If you've ever taken an economics class, you notice that a lot of times you cannot have a closed form expression for what you want in terms of your inputs, and you have to run lots and lots of simulations. If we have a closed form, we can say, well, if I now change x by this, I know how much everything else will change by. So what we want to do is we want to find the values of A and B that minimize the error. So we need an extension from one variable calculus. So I will talk about how you do all this in the advanced theory lecture that will be next. And after doing a bunch of algebra, if you're comfortable with matrices, here is a matrix equation for the best fit values of A and B. Or if you want expanding everything out, here's the best fit values for A and B. So they're going to be a bunch of sums of the numbers 1. So it'll sum over the number of data points. We have big N data points. And then Xn and Yn, Xn will be the observed input, Yn will be the observed output. So it's a beautiful formula. It's explicit, it's clear. It turns out this can be generalized. So if you have more than just 2 unknown parameters, more than just A and B, if you want to do the best fit parabola or more involved shapes, we can do that as well. It turns out you can handle nonlinear relationships as well by doing a change of variables and logarithms. So we'll see all of this stuff when we get to the advanced theory. But the point here was to just give a quick introduction to what regression is. It's trying to find the best fit line, or more generally the best fit curve, to given data. It depends on how we choose our error, what our best fit is going to be. What we will be concentrating on is the consequences of the method of least squares, where we can use calculus and get explicit closed form expressions. So this ends the first lecture.